We are now recording. Let's go back to current slide. No. Sorry about that. That was my Math 112. Okay. I wasn't ready. Okay, Chapter 4. PowerPoint Lectures 4.1. Okay. Not ready for this yet, but I'll get it set up for when we do. We don't need a projector yet, so I'll turn it on in a minute. Let's talk safety. There's 3 areas of safety you sort of need to always have kind of in the back of your mind so you'll know what to do if something happens. What 3 areas might they be? Oh boy, you got all 3. You've been in my class before. Okay. Let's start with fire. It's one you said first. Okay. Let's take sort of one of the worst case scenarios. Let's say that the fire, we are the first to see it. Say smoke starts billowing out of this mechanical room next door, through the vents here. So we're the first to know about it. Or let's say my computer just blew up and caught my papers and desk on fire. What do we do? Say again?
Jump out the window.
Okay. He can jump out the window. The rest of no. Okay. No. Okay. Few things we have to do. One thing, getting outside, that would be good, but don't jump out the window. Okay. But before we leave, we need to do something. Remember, we're the first to realize it. Say again? Oh, very good. Who might be good people to call? Say again? Okay. Actually, the best people to call would be campus security. Okay? Campus police. If any of you have your cell phones, that's a good number to have speed dial, in your thing. Go right to it and call campus police. If you don't have that in your cell phone, then the next best would be 911. Now, if you have the front desk, that would do okay too, but campus police or 911 would probably be better, okay? Campus police, number 1, better. They'll call 911, but they can respond more quickly, okay? So that's one thing, call. Excellent. Another thing we ought to do. Okay, yeah, we definitely going to leave the room, but before we do, what also should we do? Say again? Okay, yes. Try to put out the fire, or at least I will try to put out the fire, unless I was standing too close to the computer when it blew up, and then one of you will need to try to put it out. But I'll try to do that. But the question then is, where is the closest fire extinguisher? Yes, right here. You can't get much closer than that. If you go out the door right here, believe it or not, you walk past it every day, 5 feet from where I'm standing is the fire extinguisher. Right there, okay? So, yes, somebody's on the phone calling campus security or 911. Another person is trying to get that fire extinguisher. Don't some of you have always think, man, I wish I could break that glass and get it out. Wouldn't that be fun? No, y'all don't think that way. Okay. But you can do that. Now, if you don't want to break the glass, I'll go do the break of the glass. But if I'm able. Okay. So there's another thing we need to do. Call somebody, get the fire extinguisher. Anything else before we leave the room? How about the whole rest of the building? Our building's on fire, folks. Fire alarm! Yes, we need to tell somebody besides the phone. Now, they'll probably do the fire alarm too, but we can do it even quicker. Where is the closest fire alarm? Any ideas? Okay. Here we are right here. This is the second floor here, in the corner room here. This part here that's indicated by this hall that goes down a half flight of stairs and to the end, and then this long hallway this way, and then you take a left and go. It makes a big horseshoe here. That part of the building is the oldest part of the building, built before fire alarms were required. So don't go looking on any of these floors here for a fire alarm. There's not one. Okay. Now, this group here, why they put it here, I'm not sure, because this is really first floor. This is what I call the nursing wing. Okay. A lot of nursing classrooms here. Actually, one of these they made it They may have some fire alarms there, I don't know, but it's sort of far from here. Closer than that, and I know they're here, if you go out the door here, take a left, go down that half flight of stairs, right past the restroom, take that corridor across that goes right to financial services. You know where that is, right? As soon as you walk into that newer wing there, right there on that wall to the left of the fire alarm, and I think there's one right over here somewhere. That's the closest right there. That's the one you go to. I know the secretly, y'all probably know. Wouldn't that be a little fire alarm? But don't. You know, so that's what we have actually happens. Okay, so we do those three things. Call, fire extinguisher, fire alarm. If we're the first to identify it, we need to try all three of those. You don't have to worry about the fire extinguisher. I will man it if I need to, if I'm able. But the other two, y'all need to be doing as you're leaving the room. Well, where do we go? What do we do if there is a fire? Now, this is not even coming from this room. We hear the fire alarm. Where do we go? Well, we go out of the door here, take a left, go down the half flight of stairs, take an immediate left then, go down one more flight, and then head out of the building. Okay? If there's a fire in the building, you want to get out of the building, like you said, but not out of the window. Okay? Now, where do we go from there? Just to get your perspective here. Here's the interstate here. Here is Bessemer Super Highway. We're right here up in this corner of the building, right there. Okay? We go down that stairwell. There's the exit there, and we go down to that parking lot, right down there. Okay? Now, I think the grassy area here would be nicer rather than the parking lot. But they tell us to go to the parking lot, we go to the parking lot. Now, one reason I'm saying all this is last term they started what they will say. They told us we're going to be every term having a fire drill. Okay? Were y'all here last time? Huh? Well, it was on Monday, Wednesday. If you didn't have Monday, Wednesday classes, you weren't here. Okay. It was Monday, Wednesday. It was I don't remember which of the 2 days, but it was my 8 o'clock class, so it was fairly early in the morning. And what they told us to do is go to the back parking lot and all go out the same door. And I said, no. If there was a fire, you go out the closest exit. Now, if you want us all in the back parking lot, we'll go there from there. But you don't go out the same door. That's practicing bad behavior, okay? Wrong behavior. Practice what you're supposed to do. So I took my class. It's the only one who did, I think. I took one and went out the door we were supposed to go out and said, that's where we'll normally go. They want to talk with us back here. This is just a drill. We'll go back here. But I vehemently refused to practice wrong behavior. Okay? And maybe I'm an idiot or something, but the Jorian's here. This is your first day here, right? You still go by the Jorian, right? Okay, good deal. Poor guy, he's been in my class before. Okay. We went over a syllabus last time. The YouTube video is out there, but I haven't loaded it into the playlist yet. I haven't developed the playlist. Huh? We're not using Integrity. We're using that Screencast-O-Matic now. Okay, yeah. And I have to do it through YouTube. Okay. So I will try to get that done as soon as I can. It's not there yet. Okay. And we just have started. We did syllabus and research paper last time. Once I get it there, you can view everything we missed there. But now we'll be doing, we're doing safety now. We've already talked about, we started with fire. And I think we pretty much got it knocked. Oh yeah, the other thing. Okay. So we've got several people going different places. Somebody calling, somebody getting the fire extinguisher, someone pulling an alarm. But guess what? We all get together out there in the parking lot and stay together. I don't want you saying, hey, building's on fire, no more school today, I'm out of here. No, don't do it, please. Stay together as a group. I'm going to be the last one there. I'm either going to be in here fighting the fire, I'm going to be helping the slowest student get out. If someone's on a wheelchair, crutches or something, I'm helping them get out. I'm the last one out there, but I'm taking my roll book, and when I get out there, I have to call the roll. And if we're missing anybody, that means either me or somebody else or fire safety personnel is going to have to go into a burning building trying to find a missing person who tooled away somewhere they're not supposed to. So please stay together at least until the roll's call, and then if you want to mingle or whatever, that would be better. Okay? But we have to account for everybody. So don't wander off. Even if you went to do the alarm, find the rest of the group. Okay? I may, if it's a person in a wheelchair, have to get that person all the way down to that end of the hall to use the lift to get downstairs. But if we lose power because of the fire, that won't work, and then maybe I'll call on some of you able-bodied people to help me get that person down the steps because there's no lift that's working. We have to do what we have to do, okay? But then when we finally get out there, I hope all of you are stay together. Okay, so that's fire. Next. What was the second one you said? Tornado or weather. Any kind of weather emergency. This time we hear the siren, okay? If we hear the siren go off and it's not the drill, the 10 o'clock on Wednesdays or 11 o'clock on Wednesdays, whenever that is. If it's not that one and it seems to be a weather emergency, what do we do then? Two things to remember. Go low and go interior. Two things to remember. Go low and go interior. Where do we go from here? Here we are right here. We go out the door, take a left, go down the half flight of stairs, take a left, go down the full flight, but don't go out of the building like you did for the fire. Go into the building. When you turn around there, now the first floor is sort of set up like this one. First thing you'll see, you're almost on the lowest level when you come out of that stairwell there, inside. This one of the first things you'll see are the restrooms right there. And guess what? Believe it or not, the restrooms are one of the safest places to be. The walls are close together. You have a lot of corners. That's where the strength is. You have a weather, a tornado, stuff like that. That's going to be good. Interior and low. Now, the thing is, the restroom may not be your favorite place to spend a couple of hours if we have to stay there that long. The other disadvantage is there's no emergency lighting. If it is a real weather emergency, the odds are we're going to lose power. So there won't be emergency lighting in the restroom, but there will be in the hallway. So you might choose to go there. It's close walls. Okay. Now, right next to the restroom there, not the corridor, but there's an office there. That's the academic dean's office. Now, she's not here very much. She tries to come over at least twice a week. I don't know if she spends full days here. The associate dean may be over here some, or Dr. Briggs sometimes uses that office too. But the odds are it's going to be locked, so don't break in. But if someone's in there and they say you can come in, you ask if you can come in, they invite you in, that's not a bad place either because the walls are closed and lots of corners. Okay. But if not there, the next safest place is probably the hallway. Now, there's no corners in the hallway, but you have the walls. The walls, especially the back wall. Front wall, either wall is probably pretty good. But you do have emergency lighting. So that's probably where most people are going to congregate. Okay. Now, if it gets really crowded there or you just don't like it in there, you could go to that interior classroom. That's room 160. This room right here, the dean's office is 158. That's 160. That's a developmental math classroom, not Mr. Holloway's classroom. That's not as good because it has a lot of open space. You don't want to be sitting where Tyler is sitting because something could come crashing down. The walls are best, corners are even, no, the corners are best, walls are okay. So you don't want to be in the middle of an open room like that. Okay? But anywhere around the exterior, especially this back wall. This wall behind that, you're pretty safe on the back wall. Okay. Then you run into the glass doors that are in the hallway there. You go through those. The first thing on your right is the computer room in the library. That's a little smaller than the classroom. It does have corners, closer walls. Not a bad place to be. No emergency lighting, nor in the classroom either. So the hallway has that, but it might give you a little more breathing room. Okay? Now, right next to that room is another, I call it the research room or the reference room or whatever. That's where the globe is and the atlases and those kinds of things, books that you don't check out. That's a pretty safe room. It's interior. Now, you do have shelving there. You don't want shelves falling on you, but if you can find the wall, that would I wouldn't go any further in the library than that. Because any further in the library, you're going to be exterior, windows. And during a severe weather event, limbs could be blowing through the windows. You could either get hit by limbs or hit by glass. You don't want either one of those. So, we head down that way, safely, slowly, carefully, and we stay as a group. And again, I'm going to be the last one. I'm going to be bringing up the rear, making sure that everybody's out, no one's falling down the stairs, and stuff. And when I get down there, guess what? I call roll again. So stay together after we account for everybody, because if you don't, then someone's got to go back up into a dangerous situation trying to find where you went. And please, folks, don't say, oh, I got to get home and get the dog in. No, you don't. The worst place you could be is in a car during severe weather. Straight line winds, whatever. You don't want to be in a car. You're inside, lower interior, okay? So you stay there. I call the roll. We account for everybody. Then you can mingle among friends or whatever, okay? Find a better room, whatever, but don't go in an exterior. Okay, any questions on weather? And what was the third one? Active shooter. Sorry about this, folks. I never even thought about these things in the past. Now we have to plan for these things. Now there's a variety of things that we probably do. Now y'all will probably hear it before I will. If there is a shooting, I'm hard of hearing. I may not notice. I'm up here running my yap, stuff, and don't hear well anyway. If you hear something that you think could be gunshots, what do? You tell me. What do we do? What's that? Okay, that's a good thing to do, but before we do that, you would be doing that. Yeah, you would be doing it. What I do is want to lock this door. Now, the sad news is, of course, I've got it unlocked now so y'all can come out and go in as you want to, but there's no button here that you can lock the door from just doing this. I have to physically go out in the hall, find the key, and get it in the thing and lock the door, and then come back inside before you pull the door open. Okay. All right. So I lock this door, but guess what? There's a back entrance to this classroom. What do you do here? Now, there's sort of a good news, bad news situation here. I don't know why this is the case, but this classroom over here, I've been told before it's the fault of the night staff, the night police, that they don't know that's a classroom. I mean, it's disguised to look like a classroom, but must think it's not. It must be someone's office or something. I don't know why. They hardly ever unlock that room. I go every morning that I remember to do it and open the door. I can't unlock it, but I open the door to use that classroom. Okay. Now, if that door happens to be locked, go in there and push that door too. In fact, not a bad idea to do it anyway. Okay. But if it's not locked, that doesn't do you a lot of good except that it pushes the door too. Now, can this door be locked? Hey, guess what? This one does have buttons here on the side. You could lock this door. But guess what? It locks from this side, but not from that side. That doesn't do us any good. That locks us in, but he can still come in. So don't do that. Okay? Now, how about this middle door? Okay? This middle door has a deadbolt, but I don't have a key for it. And I don't know who has a key for it. So, we can't, no, okay. But, this third door out here, there's buttons here, and guess what that button does? It locks from the outside, so we can get out from the inside. So, if you don't open here and close that door, good idea, but also get the button on the door that leads into it. So, the door that goes into that classroom just like this one, do that. On your way back in, close this door as well. Why? Because there's a big glass in there. He can look in and see us. So close this door, there is no glass, and that way he thinks nobody's home. I'd say close this door too, and we turn off the light. Oh, we forgot the first thing to do. What's the first thing you should do? Oh yeah. If you got speed out for campus police, get on the horn. If you don't, 911. Now, more than likely, active shooter, someone else has already done it too, but let's not count on somebody else. Make sure somebody does that. While I'm doing the doors, okay, and we turn off the light, what else do we do? Get back here, okay? We all become your friends then, okay? Because we get over there. Hard to shoot through concrete block, okay? Is easy to shoot through a glass, or even a little easy for the wood, not concrete. Get out of sight, very quiet. That's what we already called already. We want them to think nobody's in here. Empty classroom, locked up. That one hopefully locked up. At least that other door is locked up. That door is closed. He hopes nobody doesn't know anyone's here. Okay? And we stay in our corner over here. We stay quiet. And we do a lot of praying. we wait until we know the people on the other side of the door. If it's security, they'll come through unlocking doors. Hopefully he won't have that. And then we're okay, we do whatever they say to do. Okay? I hate we even have to mention stuff like this. But there has been, I only know of one community college where there's been a shooting. Several of the big universities have had them, but one community, and then lots of elementary schools, grammar schools. I mean, it's been all over the shopping centers, movie theaters. Sad. Sick. Okay. So, but you need to know, you need to be thinking about it, planning in your head, not dwelling on it. But if it happens, you need to not have to, wait, what do I do? You know, already think what to do. All right, any questions? Syllabus, research paper, safety, anything we've covered so far. All right, we finally get to do some trig. Okay. And I hope that's coming on. Should have turned it. Yeah, it's on. Okay. All right. All right. It's coming up now. Trigonometry. What in the world does that mean anyway? Any ideas? Anyone know what the suffix metra, what that means? You see metra in anything. Like you can almost see a word in there. Metric. And that comes from meter. Basically it means to measure. So this is the measurement of triangles. Okay, the measurement of triangles was originally what trigonometry meant. Now, it's a lot more than that today, but we certainly do that. In fact, we will start by talking how we measure angles. It's really the measurement of angles now. So you might say that's sort of geometry too, but it's more trig, okay? Measurement of angles. Now, we're used to using degrees. 90 degrees, 180 degrees, 45 degrees. Yeah. We're used to thinking in degrees. But in reality, radians is the natural way to measure. Have y'all even know what radians are? Have you run into them before? Okay, we'll get them. They're pretty straightforward. And you can go back and forth. So, what we'll do first is describe angles. We'll tell how to measure angles using radians. And then we'll review how to do it using degrees and tell you the difference between them. And we'll use angles to model and solve some real-life problems. Every section we do has content, theory, information, how to use it. Okay? Just about everyone's going to do that. The use is where it's really important, folks. Okay. So let's start with angles. Okay. Now, what do we mean by an angle? Now, this is what I just said. Trigonometry means the measurement of triangles, and actually probably it would be better if you just said measurement of angles. But initially, trigonometry dealt with the relationship among the sides and the angles of triangles. That's where it began. Okay? Now, I don't want to say this for sure, but most of what I've read seems like it's always referring to astronomy. So they were doing some big old measurements back then. They were trying to map things like the planets and movement of stars and the moon and things like this. And those were the angles and the distances. Goodness, they didn't even know those distances, but that's where that relationships were coming into being important. Because they couldn't measure the distance, they were trying to calculate distances, even from here to the sun or here to the moon. And they did a pretty good job of it too, okay? Amazing, okay? But we're not going to be doing that much. What is an angle, by the way? An angle is determined by rotating a ray. What in the world is a ray? Okay, yeah, it's a half line. A line goes infinitely in both directions. Now, you maybe when I say line, you think line segment, which is fixed. No, a line is infinite in both directions. A ray is half of a line. You start at one place and go just one direction. That's a ray, okay? So, an angle is determined by starting with a ray and rotating the ray a certain amount. The amount of rotation, that's the angle, okay? An angle is determined by rotating a ray about the end point. I was using my shoulder as the end point here. There's the infinite part. This is the terminal part. So, about that end point, okay? Here's an example, okay? The starting position of the ray down here is called the initial side. Starting, okay. And the position after the rotation, that's where you end or terminate the terminal side, okay? And the amount of that rotation has to do with the angle, okay? Now, the end of that ray that stays in place is called the vertex. So the angle is measured from the initial side to the terminal side around the vertex. Okay? Now, if you were dealing with triangles now, and we're not, we're going to get there later, but you see if you had a triangle that was here or wherever it was, no matter how big the triangle is, this angle is still the same. But if you notice, if you put the triangle here or here, you increase the initial side and the terminal side. So here's the deal, folks. The ratio of those sides determines the angle. That's the secret of trigonometry. The ratio of sides determines an angle. That's the relationship that people developed way back. Okay? I got ahead of where we are here. The end point is called the vertex. The perception of an angle fits a coordinate system in which the origin is the vertex. Good place to put the vertex at the origin. And if you have the flexibility to it, put the initial side on the horizontal positive axis. That we'll call our standard position. Okay? Now this one obviously wasn't like that, unless, of course, you put the x-axis this way and the y-axis this way, 90 degrees from each other, then you have it in standard position. We like to have it horizontal, so guess what you could do? Take this thing and just rotate it, keeping the terminal side the same relative distance from the initial side, and there you have standard position. That's how we like to do it, okay? But you could have a situation that's not very standard, okay? But if you can get it into this, that would be your standard position, okay? If you have the initial side to be the positive horizontal axis, they call it the x-axis, I like the horizontal axis, and then the terminal side is wherever it ends, okay? Such an angle is said to be in standard position as shown here, okay? Any questions so far? Now, I don't know which to wonder about, either why we built clocks that turn this way or why we name angles and they go that way, okay? But in other words, counterclockwise rotation generates positive angles and clockwise rotation generates negative angles. It seems like they could have done something differently, okay? but this is indeed how they do it. Okay? If you're moving this way, that's a positive angle. Moving that way, clockwise, is a negative angle. Okay? So, initial side we like to have on the positive x-axis, a positive horizontal axis. If you're rotating this way, that's a positive angle. If you're rotating that way, it's a negative angle. Okay? Angles are labeled, not always, but generally, with Greek letters. Alpha, beta, and everybody's favorite is sort of the X of the Greek alphabet for trigonometry is theta. Okay? Just like if you say, what variable? X. Okay? If you say, what angle? Most of the time, theta. Okay? They love theta. We love theta. Okay? But sometimes, in some circumstances, you'll find we use capital letters for angles too, especially if you're given a triangle, ABC triangle. That's just typically how we name the vertices of a triangle, A, B, and C, with capital letters. Now, lowercase letter, we'll use the length being little a, little b, and little c. We'll get there later. So usually we look for either Greek lowercase letters or uppercase English letters. Now, whereas when you're dealing with points on a coordinate system, if you have a point right there in a plane, if you want to give me an address for that point, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, comma, 1, 2, 3, 4, 5, 6. 9, 6 identifies exactly that point, and that's the only address you need. It's there. Okay. Strangely enough, in circular trigonometry is what we're doing now. Guess what? There's a whole bunch of ways you can name a specific angle. Okay? Let's say we have an initial side here, terminal side here. You could name that by angle alpha, a positive angle, or angle beta, a negative angle. You're in the same place. Okay? So this position right here, moving around here to there, could be a positive alpha or a negative beta. So you have two different ways you can name it. You have more than that. You could have gone from here all the way around here and back to there again. Whoops, there's another way. Or this, there, or there. I mean, you could. There's an infinite number of angles you can assign to that ray. Okay? They show here, if you want positive ones, you could do alpha or beta or gamma. I mean, you could just name them, keep going ever and ever and ever. There's really an infinite number. This illustrates something that we say. Angles alpha and beta have the same initial sides and the same terminal sides in both of those figures there. They are called coterminal angles. Same initial sides, same terminal sides, but they have different values. Alpha and beta are this one, positive and negative. Alpha and beta here are both positive, but one's larger than the other. Coterminal angles. Okay? Now, is there a relationship between those coterminal angles? Yes, there is. We're not going to get to it yet, though. Okay. You want me to go and tell you what it is? Okay. Here's what it is. I think you can almost see from this one. How is this alpha related to that beta? You have gone here, one complete circle, and then gone that same alpha. So the difference between beta and alpha is one complete revolution. Now we haven't said how to measure that, but I bet you do know what one complete revolution is. What is it? 360 degrees. Okay. But how about this one? Do they differ by 360 degrees? Okay. Take alpha, whatever it is, and subtract from it 360 degrees, and guess what? You got that. So yeah, that's coterminal angles always differ by some multiple of 360 degrees. You could have gone around twice, 17 times, whatever, some multiple of 360 degrees. Now, does anyone know what's equivalent to 360 degrees in radians? You may not yet. You'll know it soon. Okay, don't worry about it. I'll tell you, 2 pi. But we'll get there later. In fact, that's what we're going to do now. Radian measure. And by the way, in the book, we are now at the top of page 263. Radian measure. Okay. You determine the measure of an angle, we know in degrees pretty much what we're talking about there, by the amount of rotation from the initial side to the terminal side, whichever way you're going. One way to measure angles is in radians. This type of measure is especially useful in calculus. Guess what the name of this course is? Pre-calculus trigonometry, okay? We're getting ready for calculus. So guess what? Get used to radians, because if you stay with it, you're going to find it. And here's one of the reasons for it. When you're doing your various operations in calculus, if you're in radians, everything works nicely. If you're in degrees, you always have factors involved, things you have to multiply by. So get used to radians. They're really handy. So how do we define a radian? Here's what it is. Remember, it's how much of a rotation you have. That's what an angle is. So to define a radian, we use I sort of snuck in before when we had a diagram here, and I said, one thing we do ratios. And that's what a radian is. A radian is actually a ratio. Whereas a degree, I'm not totally 100% sure of why we use degrees, but I think I know. There was an ancient civilization called the Sumerians. I don't know if they preceded the Egyptians or came along about the same time as the Egyptians, but they were the Sumerians. Later, they became what we call Babylonians. And you remember the Fertile Crescent, Mesopotamia, were one of the early people groups in that were the Sumerians. And the Sumerians had a number system not based on 10, but kind of based on 10 and 6. And I don't know why 6 is such a strange number to use. But if you think about it, 6 times 6 is 36, and then put a 0 on it, 360. We use it for angles. We really use it for time, 60 seconds in a minute, 60 minutes in an hour. We use 6s and 10s. We blame it on the Sumerians, and I don't have a clue of why they chose that, but they did. But radians don't have to worry with that. It's a ratio. And here's what the ratio is. To define a radian, use the concept of a central angle. And now we're going to put something on here. We're going to put a circle on the angle. It's no longer raised now, but it's the portion of a ray cut by a circle. Now this circle, we're not saying how big it is, except it has a radius of r. That r could be 1, it could be 17, it could be 4/3, it could be any number you choose to do. Irrational number, rational, square root of 3 halves. I mean, anything you want it to be. That's the radius, okay? So this circle is centered at the origin. This is your initial side. You rotate it up a certain way, and you have a terminal side. The length of the initial sides are, terminal sides are. Every side is r because you put that in the center of the circle. Okay. Now, when you rotate a radius around the circle like this, you cut what they call an arc length. If you rotate it just that much, that would be your arc length. That. that. Whatever it is, that's your arc length, right? Now, don't know the reason for this either. They always refer to arc length with the symbol S. Not X, not Y, S. That stands for arc length. It will for most things you ever do in math, S will be arc length. If this arc length cut by that angle is exactly the same length as R, your radius of the circle that you're cutting, then we say, and here's really what we say, the ratio of the arc length to the radius is your radian measure. So if this arc length is R and your radius is R, guess how many radians that angle is? 1 radian. Ratio of arc length to that. That's how we define a radian. Now, they've drawn it pretty close to scale here. And if you pictured doing another angle exactly the same distance there, and then do another one that would be here, you'd be just over 3 of those to get you to the straight line here. Okay. There's a reason for that. I don't know if you realize it yet or not, but there is a reason for that. Now, what if you went all the way around the circle? Okay? What angle did you just go if you went all the way around the circle? You said it to me before. 360 degrees, right? Now, what is the arc length of a circle? Does anyone know that? The arc length of a circle. Say again? It's the same thing as we call a circumference, okay? So the arc length of a circle is its circumference. Does anyone happen to know the equation for a circumference?
It's diameter times pi.
No. Okay. Yeah, you're really good. Pi d. You're absolutely right. Okay? Another way of saying that is the ratio of the circumference of the circle to the diameter of the circle is this irrational number pi. No matter how big or how small your circle is, the ratio of the circumference to the diameter is always that same irrational number pi. But that's dealing with diameters. We were talking about radii. Is there a relationship between diameter and radius? How would you define a diameter here? From here to here. That would be a diameter, wouldn't it? How much is that? 2r, isn't it? So here's another form we could do. Circumference is equal to 2 pi r. Okay? Now, this circumference is the same as an arc length, right? That's what you told me. That's the circumference. So the ratio of the arc length, c, to the radius r is what? 2 pi. So, I asked you before if anyone knew it, and you didn't realize it, but you know it. What is the radian measurement all the way around the circle? The ratio of its arc length to its radius? 2 pi. Now, let's go back to what I said before. If you took this angle here, and did that angle there, and then did another angle there, you're almost here. That would be 1 radian, 2 radian, 3 radian with a little bit left over. Well, what is the arc length of half of a circle? If the arc length all the way around the circle is 2 pi, 2 pi r, then halfway around the circle would be pi r. So guess what radian measurement of halfway around the circle would be pi. And what is pi? 3.1416, right? Just a little over 3. So yes, this is sort of making sense. Now, to give an idea, because most of us, I still think in terms of degree, what would be all the way around the circle, how many degrees? 360. What would be halfway around the circle? 180 degrees. Okay? And what's a third of 180? Just out of the blue. What's a third of 180? 60. So if you split this into equal thirds, that would be 60, 60, 60. Well, this is a little bit less than 60 because this and that don't quite come here. So this is a little less than 60 degrees. It's around 57 point blah, 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 blah. Irrational number, by the way. So if you ever need to think what is that, it's about 57. A little less than 60. Think that. 1 radian is a little less than 60 degrees. Okay? This is probably way more than we should be doing right now. But this is what a radian is. It's the ratio of an arc length to the radius. Okay? And here's the definition. 1 radian is the measure of a central angle theta that intercepts an arc S equal in length to the radius R of that circle, like the previous figure. Algebraically, that means that the radian measurement, theta measured in radians, is the ratio of S to R, arc length to radius. 1 radian would be when S is equal to R. Anything when S is less, it'll be less than 1. S is greater, it'll be more than 1. Okay? Where theta is measured in radians. Okay? Now, because the circumference of a circle is 2 pi r, which we just said, y'all came up with that, it follows that the central angle of 1 full revolution counterclockwise corresponds to a length of that. The circumference is 2 pi r. That's the arc length of equal 2 pi r. And then if the angle is the ratio of arc length to radius, divide both sides by radius, and you get the theta for 1 around the circle is 2 pi. Halfway around the circle would be pi. A quarter way around the circle would be all the way around the circle is 2 pi. Halfway around the circle is pi. What's a quarter way around the circle? Half of pi, right? Pi halves. Well, what angle is that? 90 degrees. There's another one. 90 degrees is always pi halves radians. Always. Get used to it. Fun stuff, right? Okay. I jumped ahead. Okay. This is what, okay, is it time? No, you just have to leave early. Huh? Other campus, I see. I'll keep recording, and one of these days I get the playlist done, so you'll be able to catch anything you miss. So you see what's going on here. Moreover, because 2 pi is approximately twice pi, 3.14, twice that is 6.28, there are just over 6 radius lengths in a full circle. So there was 1 radian, 2 radian, 3 radians, 4 radians, 5 radians, 6, about 6 1/4. Okay, about a quarter of another radian. Okay, that's the same thing we were showing before. I was saying 1 radian, 2 radian, 3, and just a little bit. That's about a little bit more than an eighth of a radian. Okay, because the units of measure for S and R are the same. If you measure the arc length in centimeters, measure the radius in centimeters. If you measure the radius in inches, measure the arc length in inches. Okay, they're the same. Then the ratio S over R has no units. It's a real number, just a number. It may be an irrational number, that's fine, or it may be a whole number, that's fine. But it's a real number. So therefore, degrees, that has a unit, the little degree symbol. But when you talk about angle measurements in radians, there is no. Quite often we'll say RAD for radians, just to remind you it's a radian. But really, the real answer is it's just a number. It's a ratio with no units. Degree measure has a unit of degree. Radian measurement really is just a number. Just a real number. All right. And these things we've already said before. Because the measure of an angle of one full revolution is S over R is equal to the S for one revolution is circumference, which is 2 pi R over R. That would just be 2 pi radians. So half of a revolution, halfway around the circle, is pi radians. A quarter of the way around the circle is pi halves radians. A third of the way, a sixth of the way around the circle would be 2 pi over 6, which would be pi thirds radians. By the way, pi thirds radian is exactly 60 degrees because it's 1/6 of a revolution. One revolution is 360 degrees. A sixth of that is 60 degrees. So pi thirds radians is 60 degrees. Pi 6 radians is 30 degrees. I mean, pretty simple stuff. Pi fourth radians would be 45 degrees because it's half of pi halves, right? So there's a lot of simple relationships here, and you'll come back and use these over and over and over again, okay? So here are the common angles that I just mentioned. Pi 6 radians, now they're not even mentioning degrees, but I'm telling you, okay? That's the same as 30 degrees. Pi fourth radians, that's exactly half of pi halves, that's pi fourth radians, it's exactly 45 degrees. Half of 90 degrees is 45. Pi third radians would be two of these. That would be 60 degrees, by the way. I shouldn't be doing this yet. They don't want you thinking in degrees, but I do. Pi halves radian, that is the symbol for a right angle. That is 90 degrees. Pi radians is straight line, and 2 pi is a full circle. And then you can do all sorts of other fractions in here too. 5/6 pi would be 5/6 pi would be 1 pi short of this, so that would be 30 degrees short of 180. That'd be 150 degrees. So there's lots of things you can play with here. We will be doing those. Okay, but for right now, start thinking in terms of radians. Pi 6 radians, pi fourth radians, pi third radians, pi halves radians, pi radians, 2 pi radians, and then all the other angles you can get by combining those. Now, again, I don't know which is the chicken and which is the egg, but it may be the reason we have to send angles counterclockwise to be positive is because somebody sometime or another said, well, let's let this be the first quadrant and let that be the second, third, and fourth. Or else they numbered the quadrants based on the angle. I don't know which came first, but this is how we refer to the quadrants of a plane. The first quadrant. What's true about the first quadrant? Second?
The points are positive.
Every point. All your x's are positive and your y's are positive. Your angles are between 0 and pi halves. Think degrees, 0 and 90, okay? But try to think radians. Second quadrant, what's true?
All the x values.
X's are negative, y's are positive. And here your angle is between pi halves and pi. Okay, think radians. Third quadrant, x is negative, y is negative. There you're between pi and 3 halves pi. And in the fourth quadrant, x is positive, y is negative. You're between 3 halves pi and pi. Okay. That's how to think of your quadrants. Okay? Note that the angles, here we get a few special names here, if I could talk. If you're in the first quadrant, your angles are always positive. If you're measuring counterclockwise, it's Well, what else can you say about it? Between 0 and pi halves, but the angles are always acute. No, little acute angles. No, never mind. That's the name. If it's between 0 and pi halves, we name those acute angles. Now, anything between pi halves and pi, we call those obtuse angles. Okay? Bigger than 90. Now, usually when we're down here, would something over here be obtuse? Well, we don't define it that way, but usually we would take the smaller number and measure that this way. So in sort of an absolute value of that, that would be an obtuse because that would be then between 0 and 90. Only it would be negative 0 to negative 90. Okay? And over here, measured from the positive x-axis, that would be, again, an acute angle. Okay, but let's not go there. Let's just think of these, acute and obtuse. Now, I don't know if y'all ever saw the movie Shawshank Redemption. It was sort of an older movie. Y'all may be too young for that one. It was a really good movie. If you get a chance, it's worth a watch. I remember there was a line in the movie. The hero of the movie was arrested for killing his wife. He didn't do it. And he was an accountant or something like that. And it was Morgan Freeman was one of the other inmates. And he befriended him. I can't think of the other guy's name. Tim. He married Susan Sarandon. I don't remember his name. But anyway, pretty good actor. But he was the main character of the movie. Morgan Freeman was sort of his sidekick. But anyway, the prison warden, it's a long story, but anyway, he called the warden obtuse, and he got thrown into things. So I remember the word obtuse because the hero of the movie called the warden obtuse, and he got thrown into solitary confinement for a month or something like that for calling the warden obtuse. Meaning, I don't know, he was not right. Okay, all right. Two angles are coterminal, we already mentioned this, if they have the same initial side and the same terminal sides. For instance, the angle 0 and 2 pi are the same angles. They are coterminal. As are pi 6 and 12 6 plus 1 is 13 6 pi. That's the same angle. Now notice the difference here. What's the difference between these two? Difference between those two?
1 0
Okay. 2 pi minus 0 is? 2 pi. Okay. 13 pi, 6 pi minus 1 6 pi would be 13 minus 1? 13 minus 1? 12 6 pi, but 12 6 is 2. 12 divided by 6 is 2. So the difference between two coterminal angles is always some multiple of 2 pi. Okay? You can find an angle that is coterminal to any given angle theta by then adding or subtracting 2 pi or some multiple of 2 pi to it, and you'll always get a coterminal angle. So let's say you had an angle 7, okay? 7 radians, okay? If it doesn't have degrees, 7, okay? 7 radians. Subtract 2 pi from it, you got a coterminal angle. Add 2 pi to it, you got a coterminal angle. Whatever you have, theta, add or subtract 2 pi or any multiple of 2 pi to it, and you have a coterminal angle. Okay? So here's how we express that. For a given angle theta, they like that theta, don't they? It's sort of like your x, okay, in Greek. Okay. For a given angle theta has infinitely many coterminal angles, and here's how we express that. For if that theta happens to be pi 6, 30 degrees, is coterminal with pi 6 plus 2 pi times n. So they write it 2n pi. But what they mean is some multiple of 2 pi. Okay? Where n is any integer. Positive, negative, it doesn't matter. 7, that would be 14 pi. pi 6 plus 14 pi, that's coterminal with pi 6. Pi 6 and pi 6 minus 8 pi. That would be coterminal with it, okay? Where n is any integer, positive or negative. We're going to be using this later. We're not using it now, but hang on to the concept because we will be using that later. Finally, we get to example 1. This is somewhere like page 264 in the text, okay? All right. For the positive angle, 13/6 pi, why do they tell you how to do it? They should just say find the coterminal angle, but they tell you how to do that. Subtract 2 pi to get a coterminal angle. Well, if I'm subtracting 2 pi from 13/6 pi, I need this in terms of 6, don't I? So it would be 13 pi 6, or 13/6 pi, minus, now if I put a denominator 6 here, this denominator here was 1, right? So I had to multiply that denominator by 6, so I have to multiply the numerator by 6, because 6 over 6 is 1. So that would be minus 12 pi 6, and what's that equal to? Pi 6, exactly. See, math is real nice, isn't it? Okay? And this illustrates this one we've shown before, so why couldn't they have done a different one? 13/6 pi is all the way around this 12/6 pi plus 1 more 6 pi, so a coterminal angle with that would be start with the pi 6 and go 1 more revolution around, add, or I'm sorry, they started with this one, 13/6 pi, so backtrack 1 complete revolution from this position here, backtrack 1, and you're left with that. 1/6 pi. Make sense? So any angle they happen to give you, you can find a coterminal angle to it by either adding or subtracting a multiple of 2 pi. Okay, that's the A part. They tell you how to do the B part too. For the negative angle, minus 2/3 pi, find the coterminal angle. Well, the easiest one is to add 2 pi to that. So you're starting with minus 2 pi over 3 and adding 2 pi to that. Well, guess what? I need this in terms of, this is 2 pi over 1. I need the common denominator of 3, so multiply the denominator by 3, numerator by 3, and that would be negative 2 pi plus 6 pi over, and you could do this over individually by 3, because 6/3 pi is indeed 2 pi. 6 divided by 3 is 2. So if you add those together, what do you get? Second? 4/3 pi. 4 pi over 3. Perfect. And that's exactly what we've got here. Remember, 1/3 pi, 2/3 pi, 3/3 pi is pi, 4/3 pi. There it is. Minus 2/3 pi is minus 1/3 pi, minus 2/3 pi. However you do it, you get the same angle. Different number, but coterminal angle. Right? Pretty easy to get coterminal angles. Okay, now, something, oh yeah. All of you have had Math 112, right? Using this text. I don't know if anyone pointed out to you before, after just about every example they give something called a checkpoint. Checkpoints are very good things to go home and work on, or go to the library and work on. As soon as you can, work on them. And if you can't get them, the reason to do them, I've just shown you how to do it. You go and do those. And if you can't remember how to do them, look at what it says there. Audio, video solutions to the checkpoints are in both English and Spanish are at larsonprecalculus.com. So there you've got a study aid at your fingertips on the computer anytime you want. If you couldn't remember how we did example 1, you've got everything there, but you can't get the checkpoint, go to larsonprecalculus.com. Every one of them has that. Now, we run out of time, and we will pick up next time with basically example 2, or right before example 2. But homework exercises on page 269 do either 7 or 9, do number 11, do number 13, do number 15, and stop there. We'll pick up the rest of them later. And guess what? Before you go, if you didn't notice it when you took Math 112, every exercise said, okay, I gave you odd numbers. Why? Odd answers are in the back of the book. But if you go to the back and still can't figure out how they got them, look at the title, 4.1 exercises. Look what else is written there. See CalcCheck.com, another website for tutorial help and worked out solutions for the odd number exercises. So you have computer aid right there. Without having to do WebAssign or anything else, you've got it right at 3. It's yours from buying the book. Okay? Go for it.